Hello Math 4411 students, let's begin Lesson 3, Subgroups. Previously in Lesson 2, we went through the groups in general, and here's a skeleton version of the summary. So if you need a review, but if you don't want to go all the way back to Lesson 2 and restudy everything, well, here is a skeleton version. Otherwise, let's go to Section 1, and here's a definition, a subgroup. Let's begin. Let G be a group under the binary operation star. A subset H of G is called a subgroup if it is a group under the same binary operation. We write it like this, as if H is less than or equal to G, but of course we don't read it like that. We read it as H is a subgroup of G, as I just highlighted in blue. And this is a notation. Most of the time, this notation will be sufficient, but in some case, we may have to specify the operation, especially when we have more than one operations flying around at the same time. In that case, we can specify the operation as I highlighted in green. Most of the time, though, that's not going to be necessary because we're going to consider one operation at a time. This operation star, restricted in H, is often called an induced operation. But this term is rather vague and ambiguous. It can be confusing because we use the same term, induced operation, in various situations. Whenever an operation was induced from another, we use the same term, induced operation. In this particular case, the operation in H came from a superset G, so from superset to subset. That's how this operation was induced. But we can consider going backward from subset to superset, some kind of extension, or to quotient set, even more complicated. We use the same term, induced operation, all the time, so it can get a little bit confusing. But what choice do you have? You just have to get used to all those because that's just a terminology that you have to learn. Luckily for you, this term, induced operation, is not really the core issue. The key issue is a subgroup and this notation. So, subset forms a group under the same operation. Okay, so much for the definition. However, that's not really a practical way to test whether a given subset is a subgroup or not. This is the practical set of criteria. A subset H of a group G is a subgroup if and only if, number one, the algebraic operation is well defined within H, or equivalently speaking, the subset H is closed under this operation. So H is closed under this operation. Equivalently speaking, this operation is well defined in H. That's the first condition. We have to have a well-defined algebraic operation in order to consider any kind of group condition. So that has to come first, and that's going to be the most confusing part, most tricky part when you have to do any kind of proof. The other two are easy to understand. There got to be the inverse, of course. There got to be the identity, of course. Identity comes first, and then inverse. There got to be the inverse for each element. And these two directly come from the group condition, so they're easy to understand, but this one may cause a bit of a confusion. And also, what about the associativity? Where did that go? Well, it turns out you don't really have to recheck the associativity because we already know it holds. We already know G is a group under this operation star, so we have the associativity of the star in bigger set G. So neither G nor star is anything new. There's nothing new there. What is new here? H is new. So we have to re-establish everything associated to H. The operation must be well defined in H. establish that. And then as far as the associativity is concerned, we already know because this is nothing new. Star is nothing new. And as for the identity, E is nothing new. But is it in H? Well, that's new. We know E is in G, but is it in H as well? And then the same thing goes to the inverse. We know the inverse exists in G, but is it in H? That should be checked. So H is new, so we have to reestablish these three with respect to H. Remember this because we're going to be using this criterion for some problems down here. Okay, let's go to an example, but these examples are really trivially simple. The first one is, oh come on, this is just too trivial. If you have just E, we have a subgroup of just one element. A trivial subgroup. Come on, that's too simple. Now here is a little bit better example. We have 0, which is the additive identity, and then Z, Q, R, C. So the integers, rational numbers, real numbers, and complex numbers under the standard addition. And we have subgroup structure like that. So to the left-hand side, we have smaller subsets. So Z is a subgroup of Q, and that's a subgroup of R. That's a subgroup of C, kind of like that. That's not the only way. How about some multiplicative groups? Start from 1, which is the multiplicative identity, and QX, RX, and CX. Non-zero rational numbers, non-zero real numbers, and non-zero complex numbers. What do you mean by this X there? Non-zero. There are some alternatives as well. I can slip in positive rational numbers before non-zero rational numbers like that. Or, okay, we have positive rational numbers here, and then positive real numbers before non-zero real numbers like that. We can consider those kind of things too. Positive complex numbers, oh, that's meaningless. That doesn't mean anything because there's no linear ordering in C. But we have alternatives. Roots of unity, nth roots of unity, mth roots of unity, and so on and so forth. The alternatives, many alternatives. They all make sense as long as you do not mix them up. Do not mix them up. Okay? For example, QX is a subset of Q. It's a proper subset because there's no zero. But this QX is a multiplicative group and Q is an additive group. So we cannot consider the subgroup structure there. There's no relation because we have two different operations. So do not mix up the operations. Otherwise, we have nice subgroup structures like this. Let's see, how about a little bit harder example? Still simple, but a little bit harder. Let V be a finite group defined like this. Remember this? Klein's four group, or the Vier-Gruppe. So we have four elements, E, A, B, C, and E is the identity. And then, well, group operation table is like this. And you can check whether this is group by checking the associativity, which is cumbersome, but you can do it. And then identity, yes. Inverse, yeah, all those. We went through all those already in lesson 2. Now, let's determine all subgroups of phi. Well, it'll turn out that there are 5 subgroups. The trivial subgroup, just E alone. Okay, that's easy. And then an improper subgroup, V itself. Okay, that too is easy. And then there are 3 more. 3 subgroups of order 2. Like this. EA, EB, and EC. We have these 3 chain structures. We can put all these together in a single diagram like this. Start from the top, come down as a subgroup, and then further subgroup. Start from the top, subgroup, subgroup. You can go backward from E, supergroup, and then supergroup, like that. But then again, there's one step still missing. Are these really subgroups? I mean, these are subsets, of course, yes, but are those subgroups? In short, you have to check these. Well defined. Okay, next. Identity. That's easy. They all have E, so no problem there. And then inverse. You can check all those manually. Let's see, can you do that? Oh, it's left to the students. Well, okay, all right. Okay. Okay, let's consider S1. And what is S1? Closed under the operation star. So, okay. Is this closed? Okay, let H be EA. So we'll prove H is a subgroup of G as follows. Okay, all right. Proof of S1. What do you have to prove? We have to prove that the algebraic operation star is well defined inside this H. Okay, what kind of computation can I think of? E star E is E, and okay, that's in H, no problem there. And E star A, which is equal to A star E, and that's A, and that's in H. Yes, let's go back to this. Symmetric with respect to the principal diagonal. So we have the commutativity. So this is an abelian group. So E times A and A times E are the same. Oh, by the way, we don't need abelian kind of thing. E times something. This is identity. So always we have to have commutativity. Never mind about that. But in any case, yeah, this is abelian in any case. Finally, A star A is E, and then that belongs to H. Yes, everything ends up with H. So yes, that completes the proof of S1. S2 and S3 are even easier, and S2 is, come on, that's really trivial. No problem there. Let's see. Okay, all right. Now how about the inverse? Let's see, something times E is E. Yeah, E times E is E. So E inverse is E, and that belongs to H. How about A inverse? Something times A is E, and there you go, A times A is E. So that's A, and that belongs to H. Okay, did you prove everything here? S1, S2, S3, all those? And we completed the proof for E comma A, as a matter of fact. How about the others? They're going to be similar. I mean, just change character A to B or A to C, and that's it. So there goes the proof. We just practiced use of this subgroup criterion. And there goes the second example there.